Okay, let me make sure I hit record this time. All right, there we go. Okay, how are we doing, folks? Good? Okay, bad. Well, it's break time, so hopefully 2 days you'll get some rest. A few announcements before we get back to looking at more synchronization features. I posted your exam grades. You should have been able to see those. I was not able to put in the comments on Moodle because I put those in a spreadsheet, and then it turned out that it's not importing correctly. So if you wanna see the comments I have on your code, you can either email me or stop by office hours or call during office hours, and I'll walk you through what happened in your case. Okay. Another thing is we have our semaphore homework due tonight at midnight. I updated late days basically so you can see if you still have any and work and use those if you need more time. Today we have an activity due. It's going to be due tomorrow at 2 p.m. So it's going to be about today's class. It's going to be due tomorrow at 2 p.m. Okay. And finally, tomorrow in class, we're going to launch milestone 2. So looking forward to that. And that's going to be due in 2 weeks. Questions about logistics in the class or anything related to the exam or anything else? Oh, makeup exams tomorrow. Same thing, 3 hours block. Started at any time. If you have less than a 60 on your exam, then you must retake it tomorrow. Okay? Because we said you need I relaxed it a little bit. We said you need a 65 or more to pass on both exams to pass in the class. I relaxed it a little bit to be a 60. So if you have less than a 60, you must retake the exam tomorrow. Questions? Okay. So let's do quickly a bit of recap. We saw last time that we defined something that we refer to as a critical section. So can anyone remind us what a critical section is? Yeah. Yeah, so we have, yep, exactly. 2 threads and same piece of code editing a shared variable. And we saw that in this case, we have what we refer to as a race condition that's happening. Right? And race conditions can be bad because your program seems to be running okay, seems to be running correctly, but then it's actually not. Right? So you're getting weird results. You're getting weird numbers showing up, and they don't make a lot of sense. So they are very hard to debug. Okay. So as a solution to dealing with these concurrency issues, we said that we can introduce semaphores. So semaphores are basically objects with value. And we said there's 2 important calls when it comes to semaphores. What are those 2 important calls? What are the operations you can do with a semaphore? Yeah. Yeah, so you can wait. So the actual syntax is semaphore, wait, semaphore, post. And what is waiting going to do? Yeah.
It checks and sees if there's anyone in there, and if there is, it waits until it becomes free again.
Yeah. So we're gonna basically decrement value. If the value is less than 0, then sleep, and then enter critical section in here. All right. And what is this post gonna do? Yeah.
Within an increment, and then it wakes up.
Yep. So increment the value and wake up top of key. Okay, so keep those two things in mind. You're going to need them later on. These two definitions, keep them in mind. You're going to leave them on later on to complete your activity. Okay, and we also looked at the concept of binary semaphores, which are semaphores that can only take 0 or 1 value. So we allow them to only take the values 0 or 1. And those we refer to also as locks. And one of the things we're going to define today is also what is called a mutex. So mutex, this comes from mutual exclusion. And a mutex is nothing but a much, much more efficient binary semaphore. Right? So what's it going to do is that you lock something, and then you enter the critical region, and then only if you unlock the door can someone come back into the critical region. So it only has two states, locked or unlocked. Okay? So we're going to take a closer look to it, but that's pretty much what we're going to take a look at today. So it's nothing but a binary semaphore, but a bit more efficient. And in the activity, you're going to see that the binary semaphore actually is implemented using a mutex. So it's actually mutex is at the origin of semaphores, not the other way. The other thing that we're going to take a look at today are condition variables, which are a way for us to communicate between two processes, two threads, and tell each other that it's time to wake up because some condition now is satisfied. So we're going to take a look at those two again today. But before we go into that and cover all of that, before we go into that, I wanted you to keep something in mind, especially for today's lecture. When you're thinking about the scheduler today, you're in a fight with the scheduler. Okay? The scheduler is going to want to hurt you the worst. So if there is a context switch that's going to happen, and that's going to cause a problem for you, then it's going to happen and it's going to cause problems. If there's a statement that you're afraid that you context switch before, after, or so on, and it's the scheduler is going to context switch at those specific moments where they're going to hurt you the most. So it's going to pick the worst time to execute a malicious erase condition, and it's going to pick the worst place in your code to make a context switch. So always keep that in mind. Very helpful for you when you're designing concurrent applications is to consider the scheduler as your enemy, and you're actually fighting with that scheduler. Right? So you want to bring up your defenses using the concurrency structures that we talked about. Another thing when we're talking about preemption is the following. Even a single statement can be preempted inside of that statement. So as we saw before, counter plus plus is actually 3 machine instructions, right? So we can get interrupted between the first two, between second and the third, before the first or after the third. It's all fair game. Even worse, on some architectures, we can get interrupted right when we're in the middle of an instruction. The processor is going to roll us back, but we can get interrupted in the middle of an instruction. So keep those rules in mind, assume the worst, and then design your algorithm. So what is a mutex? Pretty much, it's a binary lock. It's either locked or unlocked. There's nothing much to that. You either have the lock with you, or you're just going to wait for it. Multiple threads can be waiting for the lock at the same time. First, when it gets unlocked, the first one is going to be the one that's going to run. Yeah.
How is this? Well, of course, it's different. But
Yeah.
Specifically, how
Yeah, so we're going to take a look at that just in a few moments. Okay, so before we jump into that important question, the syntax for defining, yes?
Does the mutex get initialized to 0?
Yeah, it's by default unlocked.
Okay.
Yeah. So if you want to define a mutex in pthread, it's mutex underscore t, and then you call it whatever you want. 3 functions you should care about. So pthread mutex init. So you pass the address of m and 0, which is always going to be what we state, what we give by default for the attributes. So in this class, you can assume it's always going to be null. Second thing is pthread mutex lock and pthread mutex unlock. Then you pass the address of m. Yeah.
Is there, between pthread and mutex, is that an underline up there?
Yeah.
On the top?
So yeah, the actual thing is lock, unlock. Yeah.
Oh.
I just like to write them because it just make more sense for us. Okay. So the way you normally use a mutex is you lock m, you go into critical section, and then you unlock m. Okay. So one of the first more important things about differences between a mutex and a binary semaphore. So if you unlock multiple times, then nothing happens. You only unlock one at a time. You can't increment the unlocked state of a certain lock, right? So before, if I put a loop and I created a loop for 100 times and say for I less than 100 sem post, then the value of the binary semaphore is now 100. If I do the same now here, if I say for I less than 100 unlock, it's not going to be unlocked 100 times. It's just going to be unlocked once, and only one process or one thread can use the lock. Okay, so that's one of the main important differences between a mutex and a binary semaphore. So you don't risk losing the semantics of being binary, 0 or 1. Oops. Second thing is that a mutex is more efficient. So in a sense, a mutex is designed from scratch to be a very efficient lock, right? So that's its purpose in a sense. The semaphore it has to support much more wider functionality, so it has to sacrifice some of the performance stuff that a mutex has. So that's why if what you care about is only a binary locked unlocked state, use a mutex. If you need more than that, then you use a semaphore. Okay. So taking a look at how do we actually implement a mutex, this is where we're going to have to call on the hardware. You can't really do it without hardware support. So we need support for hardware. And the way we do it is using an instruction, an assembly instruction called test and set. So what does that mean? You're going to atomically, so this operation happens atomically. And the way test and set works is the following. So test and set. If I pass it int star p, what's it gonna do? And int v, what's it gonna do is gonna do the following. It's gonna start make integer tmp equals star p, and then say star p equals to v, and then return tmp. So basically, it's just going to save the old value of the pointer you pass, replace it with the new one, and returns the old value. But all of this either happens, so it's going to happen atomically. So either all of these three things happen together, or they don't. Right? So that's how you could use test and set to actually implement a mutex. You basically maintain a 0 or 1 variable, you test and set from different places, and that's how you figure out how to implement a mutex effect. Okay, so you just need a bit. It actually is a bit more than 1 bit, but in a sense, you can think of it as just 1 bit, and you're using test and set on that 1 bit. That's pretty much it. The other thing we want to worry about is that we can have multiple queues waiting. So multiple threads waiting, so we just also need a queue, and that's handled by the OS. So the same thing as we said in a semaphore, if there's multiple things waiting, post is going to wake up the first one, unlock is going to wake up the first one, only if the previous state was locked. So if I call 2 unlocks, I'm not going to wake up 2 processes. I only wake up a process if I move from locked to unlocked. Question?
Kind of, but it allows you later to the.
Okay. All right. Questions? Okay. So one thing we want to be careful about when you introduce mutexes and synchronization is the problem of deadlocks. So you don't want to solve race conditions by creating deadlocks. So I have a typo in here. This should not be here. This should be pthread create. And this is another function. That's the thread function. So basically, we have 2 threads. This is the main thread, and this is the child thread. And what we're doing is we want the parent to wait for the child. So we created a global variable called child done. Once the child done is, once the child is done, it's going to set that variable to 1. If not, the parent is going to sleep. So can you see a problem in this setup? Yeah. Yeah. So you're gonna lock the mutex here, and then go to sleep, and you're actually waiting for the child to be done so you can wake up, right? And the child is gonna try to come into here to set done equals to 1 and wake you up, but it's not gonna be able because you already have the lock on the mutex. So you already locked it. So you locked it. You can think about it this way: the parent locked the door and went to sleep, waiting for its son to come into the door and wake them up, right? But it doesn't make sense because you can't keep the door locked if you want someone to come in and wake you up, right? So that's pretty much what's happening here. We have what we call a deadlock. The parent is waiting for the child to wake them up. The child is waiting for the parent to unlock the door. So they're both just waiting forever. And that's what we call a deadlock. We're going to talk a lot more about deadlocks later on, but be careful. Never, ever, ever, ever go to sleep while you have a lock in your hands, right? So if you did pthread mutex lock, you should never sleep. You should never call pause and never do anything that causes your thread to just go into sleeping state. Okay? Because that's probably going to create problems later on. All right. So any questions about mutexes? We're not going to do an example because it's pretty much straightforward. In the activity, I'm going to ask you just to get used to the syntax to do one example with pthread mutex lock and unlock, and that's pretty much it. And we're going to use them extensively in the rest of the activity, so they're going to come up later on. Questions? OK. So next up is condition variables. So imagine a world where if you don't like how things are, you just go to bed. And then when you wake up, everything is better, right? That would be great, right? If you're stressed, and you have 2 exams, you go to bed, 2 days later you got A's on both exams, right? So that's one thing that might happen, and that's exactly what these condition variables allow threads to do. So a condition variable is a queue of threads sleeping because of undesirable state and they are waiting for someone to wake them up when the state changes. So a condition variable basically allows you to go into a sleeping state while you wait for something to change. And that can be helpful in a lot of places, as we're going to see in our activities. So one thing you might want to, or one thing to start using condition variables, again, it's pthread condition _t. That's the type of a condition variable. Again, 3 functions, pthread condition init, which is pretty much the same. You pass the address of a condition variable, 0 as the second parameter. And we have 2 new functions, pthread condition wait and pthread condition signal. So let's start with signal. Signal takes a single parameter, which is the condition variable that you want to unlock, or that you want to signal. So what does this mean? It means, oops, wake up, top of sleeping queue of C. So whoever is sleeping, waiting on C, go ahead and wake one of them up. If you want to wake 2 up, you have to signal twice. OK? So wait is a little bit tricky because it takes 2 parameters. It takes the first one is a condition variable. The second one is a mutex, that we assume you hold. And what wait is going to do is going to first unlock M, and then it's going to sleep until C is signaled. Then once it wakes up, so 3, wake up and lock again. Okay? So you unlock the mutex, you go to sleep. Whenever you wake up, you jump out of sleep and you lock the thing back again. So going back to our example, the parent goes to sleep, they unlock the door, the child comes back in, and they wake them up. The first thing they do when they wake up is they kick the child out and lock the door again. So that's the analogy you can take. Okay? So why are we using a mutex here? We'll see that in a little bit. But before we jump out of the definitions, any questions so far? Yes.
Keep going.
Okay.
Until you use it in like an example.
Yeah, all right. So we went through that. So we're gonna go back to our, much abused example, where we're gonna have a parent waiting for a child thread. A parent thread or main thread waiting for a child thread. And then we enforce this condition that the parent must sleep until the child thread is done. Just like what we saw before with the mutexes. And the question is that, can we achieve this using condition variables? So what do you think? Can we do that using condition variables? And how, in a sense? What is the parent going to do, and what is the child going to do? Which one of those functions that we just talked about is the parent going to call? Which one of those functions we just talked about is the child going to call? Yeah.
The parent, it does so it first takes control of the mutex, and then calls whatever was on the middle that unlocks the mutex.
Yeah.
And then goes in, and then the child does whatever it's supposed to do, and then wakes up the parent.
Yeah. Yep, exactly. That's what we want to do. We want our parent to call pthread condition wait, because it's waiting for something to happen. And we want the child to call pthread condition signal. So the child, when it's done, it's going to signal to the parent that I am done, you can wake up. So let's assume condition variables don't take mutices. There's no mutex associated with a given condition variable. Do you think this works? Can something bad happen with these two implementations of who's waiting and who's signaling? So this is parent, and this is child. Think of the absolute worst place that the scheduler can context switch between the parent and the child, or the child and the parent. Yeah. So if we context switch right here, and then we go into here, so done is going to be 1, and we're just going to keep going. So after that, if let's say there's nothing else here, when we go back to the child, we're just going to signal to no one and keep on going. But you're very close. So in a sense, signaling when there's no one is asleep is not an issue. Does that make sense? Okay. Can you think of something that's worse than that? Yeah.
Will it be right after the statement?
Yes. So if we context switch right here, we are in the parent, done is 0. So the parent goes into the if statement. Then the scheduler decides, well, I'm just going to context switch and bring the child in. The child is going to execute all of this. So done is going to be 1. It's going to signal, but oops. I'm not sure what happened. Okay. Okay, fine. So we didn't wait yet. So what's going to happen is that the child is going to signal. There's no one to catch the signal. It's going to go. Then the parent is going to wait. So we have a big problem, right? So that's why we do need to protect this using a mutex. So let's throw in a mutex and think and get rid of done, right? We don't need done anymore. Does this work? Does this solve the problem? Or is there anything else that might go wrong? Again, think of the scheduler as being very, very malicious. It's going to context switch at the most harmful time it can. Yep. So right after here. So if we context switch at this point, we still hold the lock, right? Because we haven't called wait yet. So the child is going to go in here. It's going to stop at the lock because it's already locked. So the child is blocked at this point, and then the parent is going to go in here and wait. So that's fine. That's a non-issue in a sense. It's tricky because it's kind of bordering on places we don't want to be in, but still we're lucky enough that we're going to survive that one. Yeah.
So the lock waits until it can get the lock?
Yes.
Okay.
Yeah. Yeah.
Would it be after the wait? Which we did a context switch after the wait?
If we context switch in here, then we're still. Can we context switch at this point if the child has not executed this? Right? So we can't, it doesn't really matter because the child doesn't exist anymore, right? So here, yeah. Yeah, go ahead.
Is the reset condition wait?
Yeah.
Is the, you know how like it unlocks the door and then sleep?
Yeah.
Is all of that atomic?
Is all of that atomic? Not necessarily. So let's put that to the side until the next problem. Okay. Something that's a little bit simpler. Think of very early. Think of context switching very early. Yeah.
Is it a zombie if you context switch and the child back?
You're getting close, right? If I finish the child before the parent has even waited, which is kind of what happens in the zombie case. If this runs entirely before we even run this statement, what's going to happen? The child is going to signal, no one's waiting. Nothing's going to happen. It's going to unlock the mutex. The parent is going to go in. It's going to wait on the condition, and it's never going to wake up. Right? So that's another problem that using the mutex and the condition variable is not going to work for us. So the solution, of course, is to bring those two together. We need the mutex, we need done, and we need to wait on the condition. Right? So now, if I execute all of this at once, then this statement is not going to work. right? It's not going to wait, which was the problem. And the other case was that if I context switch here, then I already hold the lock, so the child is going to block. So we solved both of these issues by combining them together. Neither one nor the other alone is going to be enough for us to actually solve this problem. So doing this is going to be part of your activity. This is, I think, the condition weight activity that you're just going to implement again after we have discussed. Okay. Now, for the rest, 12-ish or 13-ish minutes we have, we're going to take a look at the producer-consumer activity. So let me first explain it to you real quick, and then we'll try to cover it as much as we can. So the producer and consumer problem is the following. We're going to start very simple. So we have a producer, we have a consumer, and let's say we only have one empty spot. We have a variable, right? What the producer does, it puts things into the variable. What the consumer does, it gets things out of that variable. But for the producer, for the consumer to get, the producer must have put something in the box. Let's call it a box. And the same thing, the producer cannot overproduce. So in a sense, it cannot, if it already filled something and cannot fill it again, right? So it only fills at once. The consumer has to consume something, and then the producer can produce it. So we're going to start off by taking the case where we have one producer and one consumer. All right, so what is the problem we're trying to solve here? Or what is the issue we're trying what are the conditions that we're looking into? Yep. Yeah, so in a sense, when do we run the producer and when do we run the producer, the consumer, and then what happens if they're both kind of contending at the same time, right? So we're going to use condition variables to actually just tell the producer whenever the consumer consumes something from the box. So if the consumer comes in and consumes something from the box, it's going to notify the producer that it should fill it up again. So the producer is going to go back after that and fill it up again. Then it's going to go ahead and notify the consumer that you can consume now. And then the consumer is going to go back, consume stuff, and then the cycle just returns. Okay, so that's how we synchronize these two things together. So let's take a look at doing this. I'm just going to write in pseudocode because I don't want to write pthread mutex and pthread condition a lot. But let's assume we have pthread condition variable C, and we have a mutex M. So what the producer is going to do, it's going to lock M. So let's call this buffer, for example. So it does if is empty, or if not is empty. Then condition wait C and M. Then it's going to produce. And then it's going to unlock. Okay, so that's the simple structure of a condition variable. You have the lock, wait, unlock. And the same thing is going to happen here at the consumer. We're going to lock, but we're going to wait when it's empty, not when it's not empty. Wait, C and M, consume, and I forgot to put here. Okay, so condition signal C and then unlock M. The consumer is going to do the same. Consume, signal, and then unlock. Okay. So do you think this is going to be enough? Do you think this is going to work? So is there any place where when the context switch happens, it's going to hurt us the most? Yeah.
Because wait causes it to wait, and so if it goes, it is empty, and then it waits, or before it waits, it condition swaps the condition wait with that positive.
So you mean swapping from here?
Or yeah, I think it would work from either side.
Yeah.
Probably, but if it went there and then transferred, and it went into the middle of the wait for the other one.
Can it go into the middle of this one?
Yeah.
So because you already hold the lock, recall.
Right.
Your context switched, you still have the lock.
Right, no, but if it went into the if state, if it was already in the if statement when it went into it, pause it.
You still hold the lock. You only unlock before you wait, right? Before you sleep. So anytime before you sleep, you still hold the lock until you unlock and then sleep.
Okay.
Right? And the answer is actually you can't break this code. Right? So this is one case where everything works. For one producer, one consumer. But now, let's do this, make this more interesting, and have two consumers. And now we're going to go back to Abi's question, which is, what happens if a context switch happens inside of condition wait? So let's take a look. So I am consumer C1. I checked if, so actually let's draw it in here. This is the consumer. I checked if everything is empty, and then I waited. So I am in condition wait. C, no. So I'm sleeping at this point. C2, I don't know what's happening in C2, so we're just going to leave it on the side. And then we have our producer. Okay? So the producer did something, and it called produce, and then called signal or condition signal on C. So what's supposed to happen is that we're going to wake up the C1, right? Because it's waiting on the condition. It's going to take the first on the queue. It's going to wake that one up. But now we're going to cause a context switch where after wake up and before lock. So we said that condition wait does a couple of things. It unlocks, sleeps, wakes up, locks. So there are 4 things happening, right? I can context switch between any of those. Now, there are guards for context switch not to happen in the first 2, but there are no guards for things to nothing happening in the last 2. So I can wake up, go on the run queue, but then not get scheduled. So someone else is executing. What's going to happen here is that C2 is going to run, and it comes in, it checks is empty. Well, it's empty. It's not empty, so it's going to consume. But what did it consume? It consumed C1's share. Because the producer notified C1 to go in and consume, right? So C1 was supposed to consume that thing. C2 came in and stole it before it. So now C1 is in a bad position, right? Because it's going to come back in here, it gets the lock, it's going to consume, and probably a memory corruption is going to happen. Because what I wanted to consume is no longer existing anymore. Someone changed it, and I should have waited again for the consumer to do that thing. Does that make sense? So can you suggest a solution for this really, really, really tricky context switch? So I'll give you a little bit of a hint. The problem was that I woke up from a condition wait. I assumed that is empty is false, but my assumption turned out to be wrong. So how can I solve that? Yeah. Yeah, so only thing we need to do, we're going to switch this into a while loop. So now the moment I wake up, I get the lock, I do another check on the condition because I can't assume it's being met. I have to do that check again. And then either I go back to sleeping or I can actually consume. Questions?
Would you do the same thing to the other, if statement and the producer have multiple producers?
Yes.
Okay.
So it's a general idea. Sometimes you won't need it, but in general, always use a while loop before you call condition wait. It's the way to avoid, because if you have an if statement in here and you get a deadlock, there's no way on earth you're going to debug that and figure it out, right? How are you going to figure out that it's right after you wake up but before you lock? It's impossible, right? You have to spend hours and hours and hours on this. So it's always a good strategy to always put while loops in here. So let's continue this example real quick. We have 2 more minutes. The other problem that might arise is the following. So let's say, take this scenario, change it again. This works now. C2 is behaving well. It's not stealing C1's share. So C1 is going to wake up, consume. But before it actually notifies, C2 is going to wait. So we're going to have a context switch here. C2 is going to wait, and then we go back to C1. So C2 is going to wait, and then we go back to C1. So at this moment in time, the producer was actually still waiting again, right? Because it's going to produce, it's going to go back and rerun this loop again, or this process again, right? So both the producer and C2 are sleeping, waiting on the same condition variable. C1 wants to notify someone, and it doesn't know who to notify. Are we going to notify the other consumer? Are we going to notify the producer? What if the producer was the top of the queue? What if, sorry, the other consumer was the top of the queue? we shouldn't be waking the consumer. We should be waking specifically the producer. Okay, so that's something you're going to have to think about when you're doing the activity. The answer to that is you need two different condition variables. One for when you're empty and the producers sleep on that one. One for when you're full, and when you're full, producers sleep on that one. When you're empty, consumers sleep on the other. Okay. Remember, we have office hours 5 to 7 today. If you have questions about the assignment or today, just stop by or give me a call on Teams, and we can take it from there.